Thanks. Yeah. So, so this talk is based on joint work with Professor Dong Zhao from Chinese Academy of Science, and also Professor Guoli Zhou from Chongqing University. So both collaborators, they also attend the seminar. So if there's questions I can't answer, so definitely my co-authors, Professor Dong Zhao and Professor Zhou Guoli, they can help me to answer the questions. So the talk is divided in 3 parts. The first part give an introduction to the 3D stochastic Burgers equation, and then after that address several topics, so well-posedness and long-term behavior. We clarify this according to the difficulties of the proof. So the first part, the well-posedness and the long-term behavior for constant diffusion coefficient. I will explain what is constant diffusion coefficient. So here we address local well-posedness, global well-posedness, and long-term behavior. And then if time permits, I also talk about global well-posedness for function coefficient situation. So this is more related to probability methods. So okay, let's start with the introduction of the 3D stochastic Burgers equation. So we consider the 3-dimensional torus. So usually we write this torus like that. And then we're concerned with the following stochastic partial differential equation. We name this stochastic Burgers equation. So here, this is the equation. So the first term is differentiation of u with respect to time variable t. And this second term is differentiation with Laplacian. So this is for the space variable. And well, we name this Burgers is essentially due to we have this so-called nonlinear term. So this nonlinear term is in PD sense we call this convection term. So then on the right-hand side, you can interpret this as call this damping for Burgers equation or perturbation or whatsoever. So also we can name this as random force. Essentially, this means we have, so this U is unknown object we want to solve, and then multiplicative in stochastic sense with coefficient Bx, and then this term, so this is the noise term or the differentiation of Brownian motion. And then subject to the initial condition for this unknown object. So here, this unknown object is the velocity field and is read in 3-dimensional vector. As long as we impose this random term, so this usually this object is interpreted as a random field. So the field with some kind of randomness. So here Bt is standard 1-dimensional Brownian motion on a filtered probability space. So here, if for the audience not familiar with stochastic processes or particular for Brownian motion, essentially Brownian motion is invented by many people, but remarkably, this is invented by Albert Einstein in 1905 for the particles moving. So essentially, Brownian motion is nowhere differentiable in the classical sense. And then E2, it was E2 after World War II, developed a theory named as E2 stochastic calculus, which is enabled to define differentiation for Brownian motion. So we adopted this E2 theory here, and moreover, this E2 integral can be defined just for adaptedness of certain filtration. So here we have this filtration determined by some random information. So then essentially we want physically to have some kind of symmetry effect. So therefore we have this circle. This means Stonovich stochastic integral. So in that integral, compared to E2 integral, this is Stonovich integral, just like a Riemann-Stieltjes integral in deterministic sense, or in classic calculus. And then this Bx, so this is what we call the coefficient, differential coefficient, because if we interpret this equation as a stochastic equation, so all those, so apart from this term, so all those term involved with dt as an infinitesimal is what we call drift. And then this is what we call the diffusion. So the reason now we have, instead of deterministic infinitesimal for the time increments, so here we have space increments, which is measured by Brownian motion. So essentially, according to E2 calculus, so dBt is just like a square root of dt, so something like the square root of dt. So therefore, intuitively, you can see if we take dt as infinitesimal, then dBt is nowhere differentiable with respect to dt. So that's give you some kind of meaning when we interpret this equation in fractional calculus. Yeah, so that's I want to give some interpretation, and usually this what we call this filtered probability space is essentially we call this omega as the sample space, and then we have some information regards to the unknown object, or essentially related to the Brownian motion. And then we have, because this is stochastic process, so therefore there's some collective information from initial of Brownian motion. So that's somehow the technical framework from stochastic analysis, and then we have some kind of probability. So in most of functional and analytical approach, so omega can be taken as the path space of this unknown object, so that you can use Kolmogorov consistency theorem to build up the solution U as a canonic structure of stochastic process, provided this omega is the path space of this. So there are plenty of studies of path space or loop space for Brownian motion, for Clit equation, or for many different topics. So here we focus on this. So essentially, what is our stochastic Burgers equation is the initial Burgers equation perturbed by a noise. So if you don't like this formulation, if you divided this equation by dt, so then you will right-hand side, you get the standard Burgers equation. So then right-hand side, you encounter dBt divided by dt. So then this can't be defined in the deterministic sense because dbt behaves like a square root of dt. When you divide it by dt, then it's always infinity. So therefore, in probability theory, we develop a white noise calculus, or essentially based on white noise calculus, we also have Malevin calculus to use some kind of smoothness of, in hot sense of BT, to recover the adaptness in ether sense. Or most recently, it's the group in Britain, led by Oxford, what we call this rough path theory. So all in all those E2 calculus or Malevin calculus or rough path theory, they all want to give a good meaning of this stochastic differentiation or stochastic integral. Okay, so that's the equation. Let me just give some kind of background as why we were motivated to start this topic. So the deterministic model was first introduced by Bettman and then mathematically studied by Burgers. Therefore, we have this name, Burgers equation. And this model is used to describe both nonlinear propagation effects and diffusive effects occurring in various areas in applied mathematics, in particular in mathematical physics, so such as gas dynamics, fluid mechanics, nonlinear acoustics, and more recently, since in literature also studies use Burgers equation modeling traffic flows. So essentially in Hong Kong, in London, this is a serious problem for human day life. So therefore, this if we take the speed to be 0, then this is what we call deterministic Burgers equation. And then in our work, we focus on maxima principle, which in some sense can compare with the maxima principle theory in partial differential equation. So therefore, we listed some results, knowing results about maxima principle. So the first paper is by Kiselev and Lazajenskaya. Then further, when viscosity tends to 0, so essentially viscosity means if you put exponent here in this diffusion term, this Laplacian term, and let Laplacian goes to 0, so then this viscosity limit. So then there's some work to see this solution of deterministic 3D Burgers equation convergence to inviscous Burgers equation. I think Professor Tong Yang also have a very deep and remarkable result on viscous limit for Boltzmann equation. So here, this is Burgers equation is rather simple. And then further, for 3D deterministic Burgers equation, so this paper, so James Robinson and co-authors established the global well-posedness of classical solution. So then this is the reference to extend the above deterministic result to stochastic. So here in this paper, they essentially studied the stochastic Burgers equation with additive noise. So additive just means essentially, so the right-hand side of this equation, so the random term, there's no u. So it's just this equation. The right-hand side is only given by, so put this position as 1, then you will get essentially just what we call the additive noise. So in most situations, this Bx is just a constant, right? So that's in this way, they established global well-posedness for the 3D equation. So let me also just stress here, we want to discuss system of equations. It's not like a scalar equation with a multi-dimensional space variable. So there of course, there are also plenty of Bogus equation in deterministic or in stochastic situation for scalar equation. So here we want to study the vector valued. So that's we call 3D Bogus equation. So for this other side of the multi-dimensional Bogus equation or system Bogus equation, there's one situation when this equation is in potential form. So then in that case, then we can use the famous Hopf-Kohl transformation to transform the Bogus equation to Hiter equation. So this is linear equation, or to Hamilton-Jacobi equation. So therefore, this term vanishes by doing this Hopf-Kohl transformation. And then there are a lot of work in this direction, which is related to maximum in principle in our study. So our aim in this work is to extend all this to non-potential stochastic 3D Bogus equation, in the sense that the equation we considered cannot apply this Kohl-Hopf transformation. But we want to use this so-called Doss-Sussman transformation. So this transformation surprisingly also applies to deterministic equation. But originally, this transformation is designed for Brownian motion and more generally for Madingers. That's some topic in stochastic calculus. And then we want to use this transformation to study the regularity of long-term behavior for the solution. This is 3D Bogus equation. Okay, let's start with some kind of standard framework. So here we introduce this Lebesgue space. So this is P's integrable Lebesgue space. So when P equals 2, then we reduce to Hilbert space. But all these are vector valued. And then we can also introduce Sobolev space, and also this operator introduce this Sobolev space. So essentially, this is just Laplacian plus some mass or some kind of harmonic oscillators. So anyway, this is standard. Then for F in Sobolev space, we take a Fourier series, and then we can define this operator by this. So Fourier transform, then take inverse Fourier transform. So defined in harmonic sense. So essentially, this gamma 2 is given by minus Laplacian. So of course, you can make a scale of this S. And then essentially, you can define this norm. So, well, this in probability theory, we have deleted form. And then apart from this formulation, we can also define this by deleted form. So essentially, this L2 plus this together to define the norm. And then if this Bx is constant, then this is what the situation of Burger's equation driven by additive noise. Then we define this alpha t by exponential to the power minus b. This b t is Brown motion, and then we take a transformation. So this Doss-Sussman transformation is defined the vector v, which is this scalar multiply the vector u. So u is from the first equation, stochastic Burger's equation, this one. So we make this transformation, and then for v, then we derive the v fulfills this equation. So compared to the previous equation, so here with this object, then this equation becomes a homogeneous equation without a noise term. But then here, this term, so remember this one is in fact defined by this exponential. So now if it's the 1 over alpha t, then this exponential bt. So then essentially this compared to the previous equation, so this equation is rather like a deterministic equation, but then this alpha minus to the power minus 1t is random. So therefore, this is a random Burger's equation. So in some sense, we transform this equation by using this Doss-Sussman transformation to convert stochastic differential equation to random differential equation. So by random equation, we mean it's partial differential equation with random coefficients. Yeah, so that's the fundamental starting point for our work. So here, with this, we can make a certain kind of a comparison of our result or our findings. So when b is 0, then essentially this is deterministic Burger's equation. So then the maximum, we know that the maximum principle can be applied to the local solution because essentially this nonlinear terms non-Lipschitz, but locally due to this certain regular condition. So we can always have a local solution for Burger's equation, and then use the maximum principle, we can get the global existence of deterministic 3D Burger's equation. So when b is not 0, so in that case it's a stochastic Burger's equation, then the idea is to apply similarly the maximum principle to the random Galerkin approximation, and then try to establish some kind of a priori estimates aiming to establish globalness, global existence of the solution. So as long as the stochastic equation is involved, then there's a rich theory about the solution, view the solution as a stochastic process or random field. So then we know when b is 0, so deterministic Burger's equation, there's no long-term behavior. So we'll discuss this later briefly. And then when b is not 0, so then we can derive ergodicity for the random field or the random solution. So therefore, this somehow want to convince you that there's some different result for deterministic and stochastic equations. So here, let me just explain what is the solution. So the solution formulated in probability sense. So here, if the initial is either in this sublet space or in that space, which is measurable with the first sigma algebra in the filtration, because this is initial, so should along with time t equals 0. And then we see a pair is a local strong pairwise solution to this random Burgers equation. If this tau is a positive random variable, then you take, so this is t minimum with tau. Remember, this tau is random, satisfied 2 in the weak sense. So essentially just take the test function and then makes this in the PDE sense of weak solution using text function. And essentially we can make further regularity for this weak solution, local solution, because here we just take the cutoff for the time, not beyond this time. But then the solution is with this. So if the initial start from H1, then this is the regularity. If the solution is H1 half, then you will end with this one. And then also the regularity for the derivative along time is given like this. And then we also have uniqueness in strong or weak sense. So this is the formulation. We use probability, or we use almost surely, or we use in distribution sense. So I hope this is standard. And then from local solution, we can immediately lead to maximal solution or global solution. So also in strong sense or weak sense. So the maximal solution is essentially given. So we have a positive random variable which may take an infinity for a certain omega. So that's something called left-hand in stochastic processes. With this pair is maximal solution if so we have a random variable, positive random variable, which is less or dominated by psi, such this is a local solution. So then if there is a psi fulfills this, then we call this maximal solution. And then maximum solution, pairwise solution is global if this random variable take infinity almost everywhere or almost surely. So that's will be global solution. So if this condition is not fulfilled, then we call this maximum solution. Okay, so that's the concept. So now let's talk about well-posedness long-term behavior for the equation with constant diffusion coefficient. So in the equation we have for this b. Let's quickly to see this b x. Now bx is just b, which is constant. And then we want to start with the Guoli approximation for the random Burgers equation, because we use the Doss-Sussman transformation to transform our stochastic Burgers equation to random Burgers equation. So that's we name 2, and then we perform a Guoli approximation. So it takes the projection because this is not random, so we can do this straightforward. And then when we, for this approximation, we take the general term Vn, then we have a locally Lipschitz system of random ODE equation. Random ODE means that for this equation, we always have this random coefficients. And then somehow we can derive the certain regularity for Galerkin approximation so that we can take the limit. So then the first component we need to establish this Poincare inequality for Galerkin approximation. So essentially, we have this inequality. So maybe you see this is bounded by this, and then if taken V equals 0, then for U, so that's essentially come back to U we will have. From here we can get that one. And then further, this is the comparison for the Galerkin approximation term. So then essentially with this now, with this result, we can show the maximum principle for the solutions of this equation. So essentially, we can derive this one. So maximum principle just said that the solution is bounded by initial for each term Vn in the Galerkin approximation sequence. Yeah, so I'll skip the proof. So with this maximum principle, then we can establish the global well-posedness of 3D Burgers equation, stochastic Burgers equation, so equation 1. So then the step is more or less similar as for deterministic equation in PDE sense. So the first step is to apply maximum principle to Galerkin approximation to establish the energy estimate in H1. And then for initial data, try to find a subsequence of Galerkin approximation. So that's the second step. Then for initial data, then we try to find a subsequence in this convergence to this space. So remember so here for this, the definition of the norm in previous page, we definitely need this H1 and H02. And then further combine these two, then we can get that the local strong solution will not blow up for any finite time. So then this means the strong solution here. So that's the step. And to realize that, then we first apply the maximum principle to Galerkin approximation. So then you will get this inequality. And then from there, we immediately get a local well-posedness of strong solution for equation 2. So that's the transform random Burgers equation transformed by for the stochastic equation by Doss-Sussman transformation. So then pass on with this, we get local well-posedness of strong solution for the random Burgers equation. Yeah, so I will omit these details. As you can see, they still need a lot of calculation. So this was essentially completed by Professor Guoli Zhou. He spent a lot of time to do this calculation. So then with this lemmas in hand, then we can get global well-posedness of strong solution to the random Burgers equation. So it says that if we have this initial condition in H1, then for any operator given T, then there is a unique global strong solution, which is also pathwise unique. And then parallel to that, if we start our initial condition in H1 half, then we can obtain the weak solution, global weak solution to the random Burgers equation. So then the idea of proof here is mainly in stochastic analysis. So the typical step is to introduce Ornstein-Weinberg process to translate the problem into a new Cauchy problem with initial zero initial data. So essentially just transfer this to make the initial to be zero. Then we can get a global existence of weak solution by the previous procedure. Just like in partial differential equation situation, you just use Doss-Sussman transformation. So to transform non-homogeneous delicious data to homogeneous by Doss-Sussman, then you will try. With this step, then we apply the global existence of strong solution to the local solution. Then we establish this global existence of weak solution. So this is very typical in SPDE. And so that's the main scheme. So I think due to time constraint, maybe I just skip the details. And also we have this smoothness of solution to random Burgers equation. So essentially as we get before, so this solution for random Burgers equation belongs to this class, okay? So we can now just briefly talk about long-term behavior of 3D Burgers equation. So here, let's just start with the observation. So no long-term behavior of determinist model is observed. So this is, say, if we consider the classic Burgers equation, 3D Burgers equation. So then we use energy estimates, then you will get this inequality. So then further use ground-wall inequality, you get this. So then, as you can see, this is increasing exponentially along time t. So therefore, for deterministic equation, there's no long-term behavior. So then next we can perturb 3D deterministic Burgers equation by a damping term. So this is probabilistically, we always try the deterministic force, and then we try to replace deterministic damping by random term. So that's a natural way to introduce a stochastic differential equation. So here, based on deterministic Burgers equation, now we make a perturbation with a weak damping term. So given by this one, so this B is constant. And then we perform a similar argument. So then we get this. And then here we'll get a condition because here this there's a negative term here. So therefore, we can make a condition to see if this B, the absolute value of B is greater than the initial, the norm of the initial, or the first eigenvalue of this Laplacian is big enough, then there must decay estimate for U1. Yeah, so that's some kind of hint as we want to introduce to replace this damping term by random or by noise, so that there's a room for stochastic analysis to implement it here. So essentially, applying this Doss-Sussman transformation, then you can explicitly to derive, because no matter it's deterministic or stochastic, here we just there's no dimension term, so this just applying to this. So send this equation, the right hand side to be there, then we can apply this and derive this estimate. Then here we have this to be bounded. So provided this B is negative or this B is somehow when you fix T. So that's the way when T goes to infinity. When B is negative, then we can always bound it to this one. And then from this, we can naturally to think about this 3D stochastic Burger's equation. So now let's just, instead of consider the original equation at the beginning, we have this circle dot. So we use E2 sense. This is a true stochastic differential equation. This is a E2 stochastic differentiation. Then for this one, we can introduce this Doss-Sussman transformation. So here, well, some people also call this Gasanov transformation. So essentially, this term is a ground motion, which can be read as the integral of the derivative in stochastic sense of Bt. Then the stochastic integral has a quadratic variation given by this. So therefore, alpha t, the Doss-Sussman transformation given by this one, if we perform this to this equation, then we get a random Burger's equation. And then you see for this one, as I said, Bt behavior when t goes to infinity, just like a square root of t. But then here you have this one. So when you take infinity, this approach to there. So therefore, intuitively, just like instead of to vanish the viscosity, we can vanish this convection term by this transformation. So this somehow weakens the growth of energy from the advection term. So that's the observation, and with that one, we can have this maximum principle for V, the solutions of random Burger's equation with additive noise. And then we can use inverse transformation to get the long-term behavior of U, which is a solution of stochastic Burger's equation, so our first equation. Then we have also maximum principle for the equation, random equation, when we have Stoichkov type. So that means that we replace E2 integral by Stoichkov integral. So use some kind of symmetry property. So then there we can get this inequality or boundedness. So then we can further transfer this back to the solution of stochastic equation. And here you see for this, so if sufficient, there exists sufficient small epsilon, then we have this inequality. So for this inequality, when we want that t equals to infinity, but then this part could be negative index. So therefore, this could be approached tends to 0 to make this long-time behavior to be true. So I will skip this proof, and also we can derive this Lipschitz continuity. This in deterministic sense, this is clear for PDE, and this is also important in stochastic sense because this also derive the Filler property to view this random field as a Markov process along the time evolution. So then this is what we have this Filler property. So essentially mapping this Sobolev space data to continuous space data. So that's somehow in SPD we call noise improve the regularity. Essentially, this is Filler property in stochastic analysis. And then moreover, we also have this ergodicity for the solutions of stochastic Burgers equation. So that's the essentially we get a unique invariant measure to stochastic Burgers equation. So this is some results more on a probabilistic side. Okay, I think I'm sorry, it's already 50, maybe 5 minutes, Professor Liu.
Yeah, absolutely, Professor Wu. Please take your time.
Thank you. I'm sorry, you.
It's okay. Absolutely fine.
Okay, thank you. So let's briefly talk about the global well-posedness for function diffusion coefficients. So essentially, as an inference over time, so now we want to have this bx. So why we want to consider this one? So the story is that this work was submitted to a journal, and then the referees, it seems that referee think it's straightforward, that this method we invented could apply to this situation. But then it turns out this is very complicated, and in our thoughts, we think this also reveals certain kind of intrinsic or new conditions. So let's just see what the situation for this case. So now we want to consider stochastic 3D Burgers equation with multiplicative noise, means this term is here linearly appeared in the coefficients, but then this bx, so b is no longer a constant, but depending on space variable. So here at the moment we take this to be a smooth function. So it's very much hope that we can reduce this. Maybe at least the constraint of method, we need this coefficient to be smooth. So then we introduce lambda, this one, and then v hat, which is the Doss-Sussman transformation of U. Right, so then we have equivalent formulation of this equation here. So you don't need to see this clearly. I just want to indicate when we have b is a function of the space variable, the equation becomes more complicated with extra terms, because we have conversion term, which is vector multiply with the vector. So therefore, when you do this gradient calculation, then the equation becomes to be this. So here, then it's bad, but it's also good because we can implement a lot of properties of Brownian motion. So that's our idea. So then essentially, the first thought is that we want to drive maximum principle. So then for maximum principle, then there are several extra terms which we need to control. At least we need to have this non-negative guarantee for all those terms. But they are Brownian motion. So Brownian motion just means it's starting from 0. It's with equal probability, can be negative, positive, or it can be everywhere. So Brownian motion is a irregular path fulfill the full space. So if we take one-dimensional line and Brownian motion lives on this, then with probability this Brownian motion visits anywhere. So therefore, in order to have all those involved terms to be non-negative, we need this or that one to be 0. Because if they are not 0, then Brownian motion will definitely bring this term to be negative or oscillating. So that's the idea. In order to guarantee this, then we find that this is a condition, extra condition for Bx. So then with this as a starting point, then we need to compute this more explicitly. So this is just like this vorticity formulation. Well, it's not similar, but in that spiritually. So we try to formulate this in order to show this to be 0. So with this, then the equation can be simplified. And then once we have this positive or non-negative condition for all those Brownian motion terms involved, then we can have local well-posedness of this equation, simplify the equation, and also we can have local well-posedness of this equation. So this is Doss-Sussman transformed stochastic Burgers equation. And then further, we can get maximum principle and global existence uniqueness of strong solution to this. And then further to the weak solution, provided you start with different initial condition. And then from this, as you can see, we get back to this equation 8. Yeah, so that's the trick. I think just briefly to mention this. So this part, I think there's still a lot to do in order to give some kind of intrinsic meaning for this condition. So these several references, and I will just let you know if someone interested can follow this kind of references, and then to compare with this. Okay, thank you very much for your attention. I'm sorry to use up the time. Thanks.
Okay, thank you, Professor Wu, for the wonderful and highly inspiring talk. Now, next is the Q&A. Any questions or comments from the audience?
So maybe I start with a very simple question. Because, yeah, so first, thanks for the wonderful talk. So
Thank you. Thanks.
I am not in this area, so I am confused. So you emphasize a lot, the whole talk on the 3D setting. So I know that if in terms of function space or decay rate, 1D, 2D, 3D, or ND are different. So is it possible? So some of these films hold for other dimension or only 3 dimension?
Yeah, that's a very good question. So let's see. So for 2D dimension, so essentially this term behaves more nicely than 3D or 3D or ND, 1D greater or equal than 3. Then so this term together with the Laplacian, so 2D Laplacian and the 3 or more than 3-dimensional Laplacian, they behave differently if you look at the Green's function. And then this also behave differently.
I see.
So therefore, 2-dimensional theory compared to 3-dimensional, they're rather simple or doable. My feeling is they're similar like Navier-Stokes equation. So it's 2D, you can do a lot, but then for 3D, you encounter more singular object to deal with rather than regular.
I see. I see.
Yeah.
So all these film holds for n-dimensional n greater or equal to 3, maybe.
N greater equal than 3, then concretely the inequalities or apparent estimates depending on n.
Okay, I see.
Right. Yeah. So that's
maybe
very good. Yeah.
Okay.
So then it's really a hope for the people doing SPD is try to induce by the noise.
Okay.
So a la Martin here. So he's just using this. He doing this heavy machinery or this regulatory hierarchy. But then concretely, if you introduce certain kind of noise and then try to have solution in stochastic sense, and then try to link this with PD sense.
Okay, I see. Thank you.
Thanks. Yeah.
Thank you.
Okay, thank you. So any other comments or questions from the audience?
Hi, Professor. I have a question.
Thank you. Yeah.
I want to see the part of the non-behavior of I want to have a look at the non-behavior of the deterministic 3D Burgers equation. The sign of the damping, such as the sign of B, must be negative.
Yeah. I think here. Yes. Yeah. Yeah. This B must be negative.
Yes.
Yes. Yeah. That's right.
Please refer to the next page. Yes, here. So
yeah. Thanks. Yeah.
The damping BU, the sign of B must be negative. So it can give some good properties for the solution of the Burgers equation. When t goes to infinite, the energy of UT goes to 0. But in the stochastic case, it seems there are no demanding of the sign of B.
Very good. Yeah.
Please refer to the stochastic case. Yes. Please see the equation 6. Equation 6.
Let's see. Yeah.
Equation 6.
Yeah.
Here. So I I say there is no restriction to the sign of B in equation 6.
Yeah, that's a good point, Guoli. So here, because in this situation, you take this Doss-Sussman transformation. Actually, this correction term, this dominates the long-term behavior, because BT behavior when t goes to infinity, this BT just like a square root of t.
Okay.
But then here this dominates this one.
Okay.
So therefore, you take an inverse. You don't need B to be positive or negative. It's as long as non-zero. Then this always give you long-term behavior.
Okay,
So
sure.
the trouble term approach to zero. Yeah, that's a good observation. Yes.
So there is a difference between the deterministic case and the
Equation and stochastic. Yeah. So the damping. Yeah. Let me just maybe summary. So the damping term for Berger's equation, if it's deterministic, then we require this B to be negative. And then for stochastic, then you don't need this condition for B to be negative, because Brown motion will make this term oscillating. So then a certain kind of regularity of using this powerful transformation. Then on one side, we vanish this term and then make the equation to be random deterministic equation. Random determinism means differentiation in deterministic sense. But then this object, due to the property of Brown motion, this object always have a property, the inverse of this is approach to zero as t goes to infinity.
Okay.
Yeah, that's a good point, Guoli. Yeah.
Okay. Professor Wu, I have another question. I say there is a Doss-Sussman transformation below the equation 6, but it is a beginning part when you prove the double well-posedness. There is another Doss-Sussman transformation. The two seems different.
Right. Yeah. The concrete expression. Right. Let's see. Yeah. Let's see the second question.
Here.
Yeah. This one. Yeah. So there's no quadrilateral variation here. So this is just performed by the exponential BT. So this is a non-negative. Then so here, if this is constant, we use this one to transform the this equation to. So this is essentially due to different type of noise. So either you use Stonovich or use E2. Use E2, then we need to have this correction term. So this is plus b squared over 2 times t. If it is Stonovich, then the transformation is just given by this one. Yeah, that's a good point too. Yes.
So the two Doss-Sussman transformations are different.
Yes. Yeah, because that's treats different stochastic term. Because here for equation 1 we have Stonovich stochastic differentiation. So therefore, when we perform this Gasanov transformation, you already accept this quadratic term inside the equation. So that's some kind of symmetry property. Yes. Yeah, that's also good point. I should point it out. Yeah.
Makes sense. Thank you.
Thank you, Guoli.
Okay, thank you. Any more questions or comments? All right, so Professor Wu, I got maybe a very simple question. So you, so according to my understanding, you always work on the torus with the periodic boundary conditions. So how about if one work on the general domain, say a boundary domain with this non-homogeneous boundary condition? Was there any new technical difficulty arise from this kind of new setup?
Yeah, it's very important. So this is very hard.
Oh, okay.
This is very hard. So essentially, you can figure out. Let's figure out the situation. If you have the general domain with boundary condition, even delicious condition, still we need to transform this somehow to the equation. Either we use Doss-Sussman principle or use this Doss-Sussman transformation. So then the equation will become some kind of variable coefficient equation. So therefore, if you apply stochastic to differentiation, then we have this chain rule replaced by E2 formula. So then there are some terms, just like we have seen that when we have variable coefficients of B for the noise term.
I see.
So there already is complicated. So now if we have a boundary condition, then if we still apply this maximum principle approach, then we have to deal with all those terms. So it might be doable, but should eventually we see this approach is obstacle, not so efficient. Yeah, that's a very important question. I think if close to PD or SPD in both directions, so we always try periodic boundary. That's the simplest one, and then otherwise we consider the whole space, RD, R3.
I see.
Yeah, but this is very important. I think it's more meaningful if you study the problem with boundary conditions. It's concrete, and they're more related to mathematical physics, real problem.
Okay, thank you.
Yeah.
Thank you very much. You are extremely patient and clear in your talk and explanation. Thank you very much.
Thanks.
Okay. Thank you. Any other questions or comments? Okay, if no, let's thank Professor Wu again for the wonderful talk. Professor, thank you very much.
Thank you, Professor Liu. Thanks.
就跟这是用口语就可以了。
对，谢谢大家。这个可能没有说的很明确，就是耽误大家听一听，就这。
太客气了。
OK， 好的，
谢谢刘教授。
谢谢，还有侯宇辉，谢谢，非常感谢。
好的，也希望就是我们多交流。大家等疫情结束了以后，大家有机会到英国来访问，到Swansea来访问。
一定，也欢迎这个您到香港来访问，杨老师也访问我。
好的，等疫情结束，我能回去的时候。事
实上，你的那个学生叫来潘，他也到我们青岛来工作了。所以
谢谢你们的大力支持，他
交流应该更多了。
太好了。他这个盼现在在德国在做这个红宝学者我希望就是能在你们的大力支持下，他能进一步的发展。
肯定的，你有你的那个支持。谢谢。
太好了，这个就是更多跟杨老师跟你跟这个大家，再加上这个学生就有更多的一个纽带。
是的。
所以呢，热烈欢迎大家在可 traveling 的情况下来英国来Swansea访问。 交流。
好的，
好的，谢谢。
好的，
那行，那吴老师你也辛苦了。那我们杨老师你来再交谈。
没有了，没东西说了。
OK，那行，吴老师，那一个 after talk 呢，你休息一下吧。
好的，
谢谢。